As ever, it's a pleasure and a privilege to be with you. It seems to me this symposium, if anything, gets better from year to year. So thank you for your support, especially the exhibitors. You know, you're a massive part of us trying to do what we're doing with our education mission, if you like. Before I actually start talking and going through the presentation that I've got, I just want you to picture in your minds a younger version of what you see in front of you. It's the mid-1990s. There's a large modernisation project going on. The modernisation project involved fitting, amongst other things, fitting new safety gears to existing lifts. When we came to the point of testing these, we did what you normally do. We tested the progressive safety gears by putting 125% of rated load in the car, sending the car down at rated speed and tripping the governor. And a reasonable number of these systems did not stop. They kept on going down. Some of them did stop, of course. So we did what you would normally do if you're a lift contractor. We changed out the safety gears for something else which worked more effectively, and we just carried on. But I'll let you ponder what the reasons for those problems might be, and perhaps that comes back into the presentation later. So very briefly, I think I want to give a little bit of background about the lift engineering program at Northampton, but I think it's familiar to a lot of people, so I'm going to move quite quickly through that. The key thing, I think, from today is to emphasize the links that there are between the academic and the industrial, between the academic and, if you like, lift engineering practice that we all find, and how we sort of build those bridges, and how we, if you like, take the practical problems that we come across in lift engineering and try and solve those, or try and inform the development of the lift engineering courses. So to do that, there's a particular topic or example, and we're going to use a simple one, the operation of safety gear to stop a free-falling lift. So we'll have a quick look at what it says in the MSc learning materials. We're going to have a look at some drop test data, which Rory will talk you through, Rory Smith. And then we're going to set some of that in the context of a dissertation, which was an MSc dissertation from Northampton, just to sort of illustrate these links. So a quick bit of background. I mean, for me, because when I'm not with a Northampton hat on, I'm with a Lear hat on. Crucial thing in this country is that we started developing a distance learning program. That was a collaboration between what is now Lear and what is now the University of Northampton. So that's now 35 years ago. Sometime later, Northampton launched an MSc in lift engineering, and as Benedict kindly mentioned, I was on that inaugural cohort in 1998, and as I can see one or two others in the room who were there. In fact, I can see Goran. And as I've nervously walked across the car park to start that around about 20 years ago, Goran was the first person I met. So I knew at that point I was in good hands. Then later on, launch of the foundation degree, launch of the HNC, and then launch of the research degrees more recently. The date that we leave off there, or should be on there, is just to remind you that Stefan Kaczmarczyk started here in 2002. And the other thing that's missing is, of course, a few years later, he started what became this symposium. So a quick pictorial representation of what we've got currently. There's the MSc, there's the research degree there. That's, if you like, the top of the apex of a pyramid. Underpinning it, the foundation degree and the HNC that I just mentioned. And at the bottom is what is the Lear Distance Learning program, something that we are now actively wanting to develop and improve not just to underpin this structure here, but also to address vocational and other training needs in the industry. So I shouldn't digress too much onto that, but if anyone's interested in that, we are very actively now thinking about what is the way forward and trying to figure that one out, because it's not a simple thing. So diving back to the MSc, it's accredited by the IMechE, so it is, it's got a professional body accreditation. It's master's level. It's a detailed academic study. As you know, we deliver it through distance learning. Distance learning has advantages and it has disadvantages. One of the advantages, of course, is that the course can be taken by individuals at their own pace. It can be integrated into their day-to-day work. And the course consists of 3 compulsory modules, 2 elective modules, in addition to doing a case study assessment and a dissertation, a research dissertation. So very quickly to list out the compulsory modules. If you're starting out on the MSc, you'll normally take these 2 first, Lift Applications Engineering and Codes and Standards. Also, there is a management element to it, and then later on, as I mentioned, case study and dissertation. And you also take 2 electives from that list, which in recent times has benefited from the addition of dynamics and vibrations and vertical transportation systems. So to support all this, we've got learning materials. And they guide the learner, if you like, through a path, but they're not terribly prescriptive. They point the learner in the direction of various reference texts, and very much for many learners, they're a start point. So people are encouraged to go and read and research and pursue the subjects in their own ways. Each learning material has what we call self-assessment questions. And I have a suspicion that a lot of students actually just flick the page over and go over to the next thing, which is a shame really, because they're tricky little questions that are set to really promote thought. And I always feel that if you do the self-assessment questions quite rigorously, you'll be in much better shape when you get to the assignments. And the assignments are, again, quite a demanding set of questions. So if I illustrate that very briefly, the Lift Applications and Codes and Standards, if you're doing those 2 modules together, you start the course, you do the first assignments. The first assignments are relatively straightforward. They guide you into the way of academic assignment writing. And then whack, the next ones you do are actually quite demanding. So in Lift Applications, we're suddenly asking people to think about trade-offs when you look at counterweight balance factors. If you change a counterweight balance, what happens to braking, what happens to traction? That's quite a demanding one. So when they go back to Codes and Standards for a bit of respite, we throw another quite tricky one at them to think about the interaction of safety components like safety gears and overspeed governors, or for uncontrolled movement. The success of any of those systems is based on the correct integration of various components. So these are examples of real-world engineering issues being brought back into the, if you like, the assignment structure to make people think and answer these practical problems. There's just a list of dissertations that have featured. There's over 70 have been done in the last, what is it now, 16 years. So I mentioned earlier that we're going to pick out a particular topic. It's to do with safety gear stopping. I don't need to dwell on this slide very long. We're all familiar with an overspeed governor and a safety gear, and we're also familiar with the separate safety components to prevent or overspeeding in the up direction or uncontrolled car movement. And unsurprisingly, they're dealt with in some detail in the course materials, which references the standards, and all that essentially says is the job of a safety gear is to be rated to prevent the free fall of a fully loaded lift. So that's worst case, hardly ever happens, does it? But the standards tell us that we have to guard against 100% rated load free falling. And that is a representation of a system with overspeed governors, two versions of overspeed governors. I mean, now I think there's a lot of electronic overspeed governors. Maybe we could show an electronic type on there, and either an instantaneous or a progressive safety gear. Again, systems that we're very familiar with. So here's an animation. So on the left, when I let it go, the lift's going to move to around about halfway in the shaft, and then the ropes are going to break. So there it goes. Right, so the car is caught by the safety gear. The counterweight becomes some kind of pile driver, I guess, and you have to go and dig it out somewhere. So that's a free fall situation. It's relatively easy to relate the safety gear force. Whoops, I didn't mean to do that. It's relatively easy to relate the safety gear force with the acceleration of the system. It's a free fall. It's a relatively simple system. When we look at something with the ropes attached, there was a little bit of counterweight bounce there. It's quite a lot more complex because there's now the counterweight there, so there are rope tensions getting involved. It's quite difficult to actually work out what the acceleration of that system's going to be unless you know quite a bit about other parameters, and even then it's hard. So that's the reason why in practice we can't assess safety gear forces by testing with the ropes attached. There is of course a case where you can do that, but that's when you can guarantee that the car deceleration is greater than 1g, and therefore you've got slack ropes. But I think someone in the room is probably more qualified to talk about that than me. So at this point, I'm going to ask Rory to come and take you through some drop test data, and I think a learning experience you got from that.
Yes.
Thank you.
So twice in my career I've felt the need to get an advanced degree, and in both cases I started a program, and after one semester I got transferred, and then so I started in San Diego, got transferred to New York, and then in New York, and I got transferred to Memphis. And so then after that, I got transferred to San Diego again, and I heard about this program, and I said, whoa, it's distance learning. I can do this even if I get transferred again. And so I signed up for this, and when I completed, about 1 year after I had completed the course, I was at a meeting in Seoul, Korea, and was a research group meeting, global, and then we had some of our engineers were actually doing drop testing of a new safety we were developing that was a 10 meter per second double-deck car safety. And we had a drop test, and this is it, and it didn't work. This one worked, okay? So you can see in this graph here, the car accelerates, the safety gear engages, and the car comes to a stop. This is the velocity curve. Then we had a second test, and it didn't stop. So what happened? You can see here that the car's accelerate. The car accelerates during the drop, and then it reaches a flat speed. It's 12.5 meters per second, and it's not accelerating, but it's not decelerating. And so then this is where it crashed, and it gives a new meaning to a reduced stroke buffer. So since I was head of the American delegation and the American group had developed the safety gear, it was, oh, it failed. You better have some answers for us tomorrow. And I said, oh, okay. And so I looked at what was happening, and I said, well, you know what's happening here is at this point, we are dissipating the change in potential energy, but we are not dissipating the kinetic energy. So I'd seen something similar to that in one of the modules that I had taken, so I keep them in that and Guide D or something I always keep on my laptop. So I get out and I read it, and I said, oh, this is exactly like a module I'd worked on with a brake, because a machine brake is a transducer. It converts energy into heat, and so that's exactly what safety gears do. And so what I said, wow, this is quite lucky, because now I know exactly from this how much energy this system is capable of dissipating. And so because of that, so then on the trip between our meeting in Seoul and our test tower, we started running calculations and said, okay, if we know what the dissipation is per square millimeter, all we need to do is increase the square millimeters by this amount, and we'll have enough dissipation to dissipate the kinetic energy. So we said, okay, that's it, and we finished up the PowerPoint just as we drove up to the door of the test tower, and I was able to present, here's the problem. It did not fail. We were lucky, and it was identified to us exactly what we need to do to increase the area of the shoes in order to make this work properly. So this is an example of where the training that I got here and it helped save my career and that of the whole team, but it also it's not just that you get education, you gain knowledge. The program makes you have to explain things, analyze things, and it teaches you how to attack problems that you haven't experienced before. And that's the benefit I got out of the program here, and that's why I recommend it so much to everybody. So, Nick, want to finish?
Thank you.
Thank you.
So we all keep learning. I'm going to try and accelerate. Yes. So if you take that first curve that Rory showed, that's a linear. So the test mass is dropped there. It accelerates. The velocity goes up linearly because it's accelerating according to gravity. The safety gear comes in there and then it decelerates the mass. Now I looked at that and I thought that is not linear. In other words, speed reduction is not linear. So my deduction was deceleration is not constant. The deceleration is greater at lower speed. How can we explain that? What can be varying? Now, safety gear force is number of gibs on a safety gear, gripping, multiplied by a coefficient of friction, multiplied by the reaction force, pushing those gibs or those braking surfaces onto the guide rail. So my sort of simplistic approach, whoops, I didn't mean to do that either. My simplistic approach is that N and R are constant. So I'm thinking is mu varying here? Is the coefficient of friction varying during that stopping phase? Now there's the same curve again, and all I've done there is fitted, I've used the curve fit feature on Excel, and that's fitted by that curve there, which is a second order polynomial, and the fit is just remarkably good. That's a ridiculously good fit. So we're very sure that that's got an element of nonlinearity in it. Now, at any point on that curve, we can take the gradient of it, and that tells us the rate of deceleration. From that, we can work back to work out the safety gear force, and because we know the clamping force and the number of gibs, we can work back to get the coefficient of friction, which is all that slide says. And if we plot now the coefficient of friction as a function or against rubbing speed, we got quite a nice curve like that. I was amazed how good that data was coming from Rory's drop test. Very, very clean, and it shows a gradual reduction in the coefficient of friction as speed increases. Now what I would say is this is going up to about 13 meters per second. That's fast, isn't it? And it's showing about a 20% reduction in friction, which is actually a very, very well behaved safety gear. I've seen 30 or 40% variations in safeties that are only at 3.5 meters per second. So setting that in context very briefly, there was actually an MSc dissertation done some years ago on friction in progressive safety gears, and the model that was fitted to the data was that, an exponential. not quite the same as a curve you just saw, but it did show that friction tended to reduce as speed increased. And we were able to set that in some context. So a guy called Klaus Fehrer from the University of Stuttgart back in the 1970s, or I think maybe even the 60s, published this stuff. So he's showing safety gear friction as a function of rubbing speed, and also some for railway brakes. There was other data that we found that went back to 1865. It was data on railway brakes. So this isn't a one-off that we found. This is an identifiable engineering technical phenomenon. So very briefly, because I've overrun, conclusions. Hopefully we've illustrated how the lift engineering provision at Northampton does tie practice and theory together. I think Rory especially did that brilliantly. We said a little bit about assessment of the MSc and how we try to tie that into real life engineering issues. We've had that example of the safety gear stuff, and we set it in the context of that dissertation. Now my final comment is that dissertation was my dissertation. I did it because of that problem I had 25 years ago, because I didn't understand why those safeties failed on those lifts back in the mid-90s, and I needed to explain that. So that's why I did that dissertation. Thank you.